Hello everyone. This is our first video in our video series on errors and measurement. You've done the investigation outside where you measured an unknown distance with your lab group. So now we're going to start to analyze what you've done when you're measuring. All right. Our objectives for this video is that you could learn a couple terms. You're going to learn precision, right? What that means, random error, and accuracy. All right, those three terms. You're going to apply those three terms as descriptions to sets of measurements. All right, so keep those in mind while you're watching the video. Now, I'm going to start off the video with a little demonstration. All right, but before we do that, I want to ask you a question. If you can see at the top, we have our essential question. Can you ever make a perfectly exact measurement? Say you're measuring, maybe you've got construction done in your house, and the doorway has to be a certain height, maybe at least 6 feet tall to fit the tallest member of your family through. Can we ever make sure it's exactly 6 feet tall? Think about that. Pause the video for 30 seconds. Think about that. Is there even small errors that could come up, and why? Alright, so I hope you paused the video. I hope you thought about that. And we're going to talk about, obviously, random errors today, which could come up. But let's get to our demonstration. This is a demonstration I like to do every year, but since I'm not here, I will just show you kind of how it works. So what I have is a baseball bat. This demonstration is called How Long is the Baseball Bat? And I have a ruler, or rather a meter stick, to measure how long it is. Now the thing about this meter stick is it is or ruler rather, is it is four-sided, alright? Why would you make a meter stick with four sides? Well, it's really just for this demonstration, to be honest. The thing that's different about each side of the meter stick is how many lines are marked on each side. So if you could see this side, as you can see, it says it's 1 meter long, right? But there's no lines marking off, well, maybe where is 1/10 of a meter, 1/4 of a meter, 1/2 a meter in the middle of the meter stick. So you can't even know that when looking at this side. However, the next side, there are 9 lines marking off 10 different sections of the meter stick. So we could know that, for instance, right here where the 1 is marked is where 1/10 of a meter is, and 2/10 of a meter, 3/10, 4/10, and here's 1/2 a meter, and so on, right? Next side, right? So each of these are decimeter long. That's how long they are. The next side has 100 lines. Okay, 100 lines on it. So each one of these are centimeter. Now you can think about how these different amounts of lines are going to cause different amounts of error in measurement, right? So I've done the experiment already. Well, I can't really do it myself. Usually what I do is I pass the baseball bat around to maybe 10 different students, and I have the students just say, for the no line side, for instance, how long is the baseball bat? That's it. And they give me their best guess at it. So I've done that here, right? I say, how long is that? You know, it doesn't come all the way to the end of the meter stick, but it comes close. So you certainly aren't going to say it's 0.1 meters long. You're not going to. It's probably more than 1/2 a meter long too, because it comes close to the end. So most students tend to guess that, I mean, at smallest, it's about 0.78 meters long. And the student who gets the largest would say it's almost a whole meter, 0.96 meters. But there's really no line, so it's hard to tell where it falls, right? Next, when we add more lines to our meter stick, we're able to tell kind of where it falls measuring wise. So take a look here, and we could see if we start at the 1, right? I guess this guy's upside down, right? Should turn him like that. We start at the 1 over here. Backwards, there we go. And we can see it goes up to about between the 8 and the 9. So we know it's 0.8 to 0.9 meters long when we add more lines. So we can eliminate the 0.78 and the 0.79, right? Those are out. We know it fell between the 8 and the 9. 7, 9, and 7, 8 fall between the 7 and the 8. They're not good. So we've added more lines and we're able to kind of narrow down our measurement to within a specific range. We're also able to throw out the 0.9 somethings because we know our baseball bat falls in between the 8 and the 9. So these are between the 9 and the 10. They're out, right? So we see with 10 lines, all our guesses range from about 0.84 at the smallest to 0.87 at the largest. And everybody's trying to get a little closer, but the third number they really don't know. You know, they're trying to get an exact measurement. Maybe one of them did. Who knows, right? Actually, I do have the real length up here that I have secretly measured with a secret method. But as you could see, we know because when we have the 10 lines and the bat falls between the 8 and the 9, all our guesses have to be 0.8 something. Okay. So we've narrowed down our measurement when we've added more lines. Lastly, we went to 100 lines. And at that point, if I could zoom in real close right here, we could see that our bat falls between the, try to get the right spot. There we go. You can see it falls between the 86 and the 87. Can you see that? Just trying to get the right spot with my hand on the other side. So because we see it falls between the 86 and the 87, we know our measurement has to be 0.86 something. So we know 874, 873, 872, 871, they're all out. Now that we've added more lines, we've narrowed down our measurement even further because we have 100 lines now. Likewise, the 0.85s are all out too, and the 84s. Our measurement is between the 86 and the 87, so we have to be 0.86 something. We have 100 lines. Lines help us narrow down our measurement to within a specific range, right? Now, everybody's like, yeah, I get this, okay? But let's apply some terms to this, all right? Let's start with this. You read about this yesterday in the book. Precision. The quality of a data set is consistent and repeatable. However, precision does not indicate the data is correct. It just means that you are able to get the same number each time. That's what precision means, or around the same number. Data that is not precise would be spread out, so you can't get the same number each time. However, it has absolutely nothing to do with whether your data is close to the real length or not. Precision has nothing to do with that. Okay, so let's apply precision to the data we have collected about the length of the baseball bat. I can ask a simple question: which set of data or which measuring method, no lines, 10 lines, or 100, is most precise? Why don't you pause the video, choose one, then start it up. Okay, so I hope you chose the 100 lines, right? It's the most repeatable measurement. It's the most consistent measurement because they all fall within a small range. That means they're very precise. All right, so we've actually have a column here for range, and range is how you measure precision of data, right? If data falls in a small range, it's very precise. So we could see 0.868 to 0.861. What's our range? You could do it yourself if you want. It's a small range, 0.007. 10 lines, what's our range? 0.033. A little bit of a larger range, less precise, more spread out, right? So no lines is even more spread out and less precise right here. So we have 0.96, 0.78. It's about 0.18, an even larger range of measurements, right? So the more lines on the ruler, the smaller the range, the more repeatable and consistent the measurement, the less guessing that and estimation that has to happen between the lines. So 100 lines is our most precise measurement because there's very little guessing. It's very repeatable. There are still guessing in between the lines. We don't really know 0.865, 0.864, which one. We know it's a 0.86 something, but there's still estimation, but it's very small. So it's very precise, very repeatable, right? All right, so there's precision, right? Here's our most precise, and here's our least precise, right? Now, what causes no lines to be imprecise, not have precision? What causes no lines to not have precision is, we're coming to our second term now, error called random error. When there's no lines on the ruler, we have more of a tendency to make random errors because an error, well, let's define random error. Random error is error which ruins precision of a set of data. It increases the range due to high levels of estimation and guessing, right? So when we don't have any lines on the ruler, what are we doing? We're estimating because we have nothing to judge by. We have no lines for our guesses to fall in between. No reference frame to make our measurement, right? So precision is really a quality of your measuring tool, right? When we say the 100 lines is very precise, what we're saying is that there's less guessing. It's a repeatable measurement. But here, there's more guessing. So you have a wider range, right? There's more random error. Random error is what ruins precision. You're going to see that random error and precision, these guys, they just don't work together, right? When stuff has precision, it doesn't have random error. When stuff has random error, it doesn't have precision. Here we've got more random error and no lines, and 100 lines we have more precision, all right? So maybe I'm being redundant, but hopefully you understand that now. One calling card of random error is because it's random. It actually, and I have a little board for this, because it's random, the mistakes you're gonna make are gonna be estimated too high, too far up, or too far down in equal proportion. So maybe Jimmy guessed 0.96. A lot of random error, too high. It was random though, because Johnny came back and guessed too low. Random error always consists of too high guesses and guesses that are too low. All right. Can we reduce random error? You should know the answer to this now. Think about it. How do we reduce random error? Add more lines. Reduce the range of our measurement. Get more precise. Right? Can we ever eliminate random error? That's a good question. Can we eliminate random what if I will just add more lines, right? Reduce the range of your measurement even more. Is that possible to get rid of it entirely, though, and have absolutely no guessing? No guessing at all between the lines. Removing all estimation. How many lines would you need to do that? You would just need more and more and more lines to reduce the range of your measurement even more, and then you get rid of random error. Is that possible? Because we're human, it's not. We always make estimations and random error. Everything we do is imperfect. So you can't really get rid of it. You could put infinite lines on a ruler, marking every number, including every irrational one too, but then you wouldn't even be able to read the ruler. So you wouldn't even be able to see the space between the lines. And all our measurements occur in the space between the lines, not at the lines of the ruler. So you could keep adding more lines, but at a certain point, you've reduced random error, but you've never ever actually eliminated it. All right? It's always there in every measurement. How can we live like this? We're human. We've kind of dealt with it. We find methods to reduce it, such as adding more lines to our ruler. Okay. I could go off on a tangent for that for too long. Let's talk about accuracy. Accuracy is different than precision. There's two qualities to measurement. There's accuracy and precision. Precision has to do with repeatability, not whether it's correct. Accuracy has to do with how correct your measurements are. It's the quality of a data set that it is centered, like it's supposed to say, as it is centered around the correct value. So I told you I have the real length of our stick here, right? And let's see if these data sets are accurate, all right? And the way to do that is to take an average, okay? So accuracy, I'm going to write that down, too, has to do with the average. If you're not writing things down, restart the video. Start writing things down. It's okay, you got the whole period, you're good. Accuracy, you measure it with the average. How do you measure precision? With the range, right? Small range, high precision, low precision, right? Lots of random error, right? But accuracy, we're going to see whether we're centered around 0.8635, the real value. So why don't you stop the video and just take the average of these three columns right now. Okay, we're back. I hope you got what I got, because for the average, I pre-calculated this for all of them. They're all 0.88, or I should say 0.863. They're all really around the real value. Now, how could no lines, how could we have so much random error here and still be accurate and centered around the real value? The reason is because our measuring method had no actual mistakes in it. Yes, we used a bad device, but we didn't, choose, we didn't, make a mistake and start at the wrong spot. We didn't accidentally choose a yardstick instead of a meter stick, or a ruler, which is a foot, and report that as meters. We didn't make any mistakes. We just didn't have any lines on our ruler. So no lines is accurate, centered around the real value. 10 lines is accurate. 100 lines is accurate as well, right? The thing is, people don't want to say, because no lines has so much random error, they want to say, oh, it's not accurate either. It's not precise. And they want to say, oh, it's not accurate either. It is accurate because, like I told you before, random error means you guess too high and too low. No lines has a lot of random error, which means we're guessing too high, some of our students, and we're also guessing too low, right? And those cancel out. The high guesses and the low guesses cancel out. So our average is still equal to the real length of our bat. So unless you make a real mistake, and you keep doing that same mistake, you're still going to be accurate. Okay, random error does not ruin accuracy. It makes the range larger. It ruins only precision. All right, that was a little long, but you're going to be good.